Our next speaker is Xiaofu Liu, who is a PhD candidate with Dr. Langley at Ohio State University, working with our knowledge-based portal core.
Yeah, so thank you for the introduction. I'm Xiaofu from the Ohio State University. Today, I would like to introduce our co-learning framework for maternal and pediatric pharmacotherapy knowledge drug discovery. Maternal and pediatric patients are usually underrepresented in the clinical trials due to the ethical and safety considerations. The distinct physiological profile of maternal and pediatric patients means that the data from the adult populations cannot directly extrapolated to these two populations. Our counting shows that within the 220,000 drug labels, only a small fraction of them provided the maternal and pediatric related guidance, which may bring the, so for the other parts, there are some potential risk in the clinical practice. So here our objective is to construct an MPRINT Knowledge Portal Silver, which is a publication-based maternal and pediatric therapeutic knowledge base. We hope this resource can integrate the scattered information, support the research, and maybe promote the drug label change. So the construction process includes three steps, which are the PubMed query, the corpus and model construction, and the large-scale extraction. Here are the three steps. Yeah. And next, we use our MPRINT Knowledge Portal Silver to apply the gap detection. So in the first step, we use all PubMed citations as the data source to filter out the maternal and pediatric related research with the keywords like that curated by the experts like this, the related match term list, while excluding the animal studies, in vitro studies, and reviews. We actually have to query. This is the first query, and after we updated the keywords and the match term list, we applied the official query and found 2 million maternal-related papers and 3.3 million pediatric-related papers to support the following knowledge portal construction. So after the query, we already collect the maternal pediatric related research, but only a few of them are maternal pediatric therapeutic research. So we developed a co-learning framework like this to allow us get the suitable labeled data set to support the following model construction with the accessible manual annotation workload. So first, we use a double annotation with the third expert adjudicated the disagreement part. And next, in the calibration stage, we compared the bioboard model predicted labels with the manual labels.
They are just starting the lightning talk.
Manually check the
we're going to be leaving to go to lunch.
Correct the potential annotation errors. Next, we use the calibrated data sets to train a bioboard model that then predict all the unlabeled samples. And based on the predicted probability, we randomly select the samples from the positive pool, uncertainty pool, and the negative pool respectively for the next iteration. And finally, based on the things we learn from the annotation and the calibration stage, our experts updated the annotation guideline. So here's the loop. Within this loop, the annotation guidelines were continuously updated. So this process made our guideline can capture our labeling objective better. And the calibration stage give us a chance to find the potential annotation error and also adapt the updated annotation guideline. So here we use a 1,000 randomly selected external test set to evaluate the performance of the co-learning process and check the performance of the model. A model we will then use in the large-scale extraction. And we have the 3 rounds of co-learning process, and we switched the class strategy from 3 classes to 6 classes and have another collaboration. And within this process, the CT got the consistent high F1 score larger than 0.8 and finally got a 0.91 F1 score. PE shows a gradual upward trend within this process and finally got a 0.88 F1 score. And PK got a significant performance improvement after we switched our class strategy from 3 to 6 and finally got a 0.91% F1 score. So with the model we constructed before, we applied large-scale extraction and got about 1 million maternal pediatric therapeutic papers. Here are some statistics based on the subpopulation and study types. So with the well-organized MPRINT Knowledge Portal Silver, we applied a research gap detection by comparing the research evidence distribution and the prescription frequency. So we focus on 5 subpopulations, which are pregnancy, postpartum, infant, child, and adolescent. Here are the landscape of these 5 subpopulations, and each row within the figure represents a drug that have more than 10 prescriptions within the corresponding subpopulation. And here are the counting. So I will use the first bar as an example. That means, so this bar means within the pregnancy population, within the drugs with more than 10 prescription in the pregnancy population, 59 of them do not have the PE or CT publication evidence, and 91 have only a few this kind of evidence. So this, we also do the pharmacovigilance analysis on the 10 drugs with least studied in the pediatric population and the pregnancy population. We found the adverse events for these 2 populations from the FIRS and the market scan respectively. And they compare with the existing drug labels, we found a lot of adverse events that outside the label shows, so which means some potential gap and the potential risk. So that's all I have today. So thank you so much for your listening.